Well, hello and welcome to the next podcast slash vlog. Um, had a fun one this week in which I had to travel about 8 hours to do a couple hours worth of work, and it was interesting because it was a fan application, and I was asked to take a look at it because I had you know overcurrent issues with the drives. They had damage to the belts, damage to the shivs. So I went down and took a look, and we used the Empower to do some of the investigation. We're going to take a look at some of that, and I may add some. I may do another step, but there's a couple of things that occurred. So this is the application here, and here's one of the drives. We have the Empower set up. So just the one phase of current. And we took data. Now, this is one of the cool things about the Empower system. We'll come back to that later. Is, as you can see here, I have 4 sets of data open at any one time. So I can actually open up all the data in order to look at separate things. So this is the first machine we looked at. And it is a 60 horsepower, 45 kilowatt machine. And you notice here that there's something going on with the frequencies. They're jumping back and forth. So they move around, and they move around quickly. Okay, so it's on a drive. We have this application. Let's go back to what we're dealing with. So I love it when salesmen become engineers, sales and marketing become engineers, because that makes me money, plain and simple. And the reason for that is we're constantly having to go out and fix things because they're given a set of talking points and they're said, go sell this product into these applications without understanding the applications. So in this case, we have this machine. It varies rapidly, so they installed this. So this is, yes, what effect, it's called a synchronous belt, or in this case, a timing belt. The other thing was, I noted, was the original dimension on these belts on the shivs were a bit different. So these are just, this is like about 11 inches across. It's about 12 to 13 inches across. The original ones were smaller and larger, so they changed the ratios. Nobody thought to change drives and everything else. Now, the system is got a feedback based upon a constant static pressure. And I had been there the prior year, and I said, even then, with the V-belts, I said, you want to make sure that you change to an S-curve, and make sure that the startup and coast down times are long enough, because a fan, especially a fan of this size, has got a lot of inertia behind it, and bigger fans even more. So changing speed is not a simple thing. It can be very, very damaging to this type of application. It's one of the reasons why way back in the day, people like myself objected to the idea of using this type of belt in a high inertia fan application because of a bunch of things. Well, lo and behold, at some point, the belt industry decided to go and have work done to show how highly efficient this type of application is, because they want to sell a more expensive belt. Now, I agree, a synchronous belt will do a lot of great things in certain applications. I am not really clear let's just put it this way. There's a lot of things you have to do if you're going to do this for this type of application. They were seeing all of the problems that we had identified back then. And this is not the first time I've dealt with this. It happens all the time. So we go in and we take a look at it. Now, when I looked at it and I looked at the drive application, here's where we start into some data. Okay. Oh, and the other thing was that these are standard ball bearings on these motors, and the belt tension is set to the belt. Now, what I'm doing here is I'm putting a lot of pressure on the belt, and I had maybe 1/8 of an inch deflection across that distance. And so we took the tuning thing to it and found out that was the minimum. That's the minimum that was supposed to go on there. Now, they've had, on these applications where they've installed these, they've had bearing failures. Well, there's, in the end, there's a lot of things you have to consider if you feel that you need to go this direction. So where does this come from? Well, other than the manufacturers, let's pull up a couple of things here. I'm going to pull up some Department of Energy stuff. And first off, while I'm waiting for that to pull up, let's go ahead and I'll show you where this information resides. I just finished updating the website over this weekend. So here it is here. Department of Energy website, energy.gov, EIEDO, that's the new subfolder. So if you were following folders before, following links before, these are all new and again, just because they want to make sure we're confused. Anyways, this is the motors, all of the stuff that we created back in the 1990s and everything else, and of course the measure tool that I've talked about before. I might do another one on that because this would be a good one to take a look at. This one, they say it's still working on. It's already done. And then here's some case studies, et cetera, et cetera, et cetera. These are all of the other ones that are associated with it. So compressed air, motor, pump, fan. So let's take a look at some of the documents. I've already downloaded them. And we'll start with the motor book. So this one here, this was the new one back in the 1990s when we developed it the first time. It was a really good gray book. I've got a copy of it somewhere. The last time we updated this was basically 2011. There I am. You can see quite a few of us involved in it. But it goes through selecting and applying electric machines, how to maintain them, looking at different issues that you run into, things like that. All of that is here. How to set up and make sure the performance is correct, et cetera, et cetera, et cetera. Now, as I've always said, what's kind of fun about this stuff is sometimes some of us get left off of the updating. So the source book for fans has a section in it. You can see it's about 90 pages. So we get into the belt drive applications, and this is where we get into the types of belts. So flat belts, sometimes called craft belts, V belts, cogged V belts. Now, these are very, very efficient because there's more effective contact surface area, more friction in it. So where a V belt might be, in the low 90% efficient, a cogged V belt will tend to be in the mid 90s. And you can see by how much slip's involved. And this assumes that you apply it correctly. And then synchronous belts. So this was all of a sudden a push. Now, the last updates I was involved in on the motor stuff and fan stuff was about 2010 and 11. Now, there was some of this discussed in 2005. It was definitely discussed in the 1990s, and everybody went, no! So if you look back then, there were very few people that pushed the idea of going to a basically timing belt. So here's where we get into it down here. So synchronous belts, that's this type here that we're looking at, and the contact area. So basically, is literally like a gear, but as a belt. Now the problem we run into is actually outlined. I don't remember if it was outlined in this section here, but it says, despite their advantages, synchronous belts must be used with caution. Synchronous belts are very noisy. This is definitely true, which often discourages their use. They transfer torque very quickly, and in applications with rapid load changes, the effects of sudden acceleration and deceleration increases wear on the driven machinery and the risk of catastrophic failure, especially when you're talking about the type of fan we're looking at. You can start to develop cracks in the surfaces and the components due to sudden and rapid speed changes. Basically, it's all based on the inertia, et cetera, et cetera. So we knew this. I mean, it used to be, as soon as they started doing variable speed, then it became more important to monitor fans that used to be designed for like 40-year life before you'd start generating fractures, because it is a relatively thin material. Synchronous belts also require precise alignment, which is difficult. Before switching or switching to synchronous drives, one should also consider belt drive vendor and review the history of similar equipment, similar service conditions. So that is there. Now, the actual tech tip that's on the website is this one here. Okay, it says, belt drives, flexibility, pulleys, shivs of different sizes, V-belts, peak efficiency 95%, and then as they get old, they can decrease by 5% for if it's 95 down to 90, that kind of thing. It says here, the proper tension of a V-belt is the lowest tension in which the belt will not slip at peak load conditions. It's always going to slip. Okay, as a matter of fact, even the belts we looked at had a slight slip to them. I know. What that means is that they're flexing and everything else. So it happens. So in any case, go through. Here's where we come up with the efficiency. We're going to calculate that directly. Further considerations. Okay, so let's see. Yeah, we're going to talk about this here real quick too. So, cost effectiveness improves when notched or synchronous belts are installed at the end of a V-belt life when changeout is scheduled. So basically, don't do it until then. Synchronous belts are the most efficient choice. However, notch belts may be a better choice when vibration dampening is needed, or shock loads cause abrupt torque changes that could shear synchronous belt's teeth. Now, in this particular case, this application has constantly changing speeds pretty rapidly, and they didn't have, and the gain was set all the way to the maximum. So these were abrupt changes set for linear. So it basically slam, 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 slam until finally they'd start shearing off the belt teeth. And then, of course, they were definitely noisy while we were doing our testing, way more than a belted application. So selecting this over a notch belt becomes a bit of an issue. So this is supposed to be the notch belt. And then, it will have a standard shev versus this type here. Yes, again, there are applications, I agree, that this would fit, but not one with rapid, fast changes, and that's a precaution. But you also note that I had to look across multiple documents to do that, and the only reason I'm aware of this is really because I had to be involved in the discussion. The other part is runs cooler becomes really important, and I'm going to show you why. So as we get into this further, let's take a look at the application. So the first thing we did is we went in, and there were no changes to the drive originally. It's shifting speeds rather rapidly We went ahead and had them reprogram the drive for an S curve, gave it a 1 second S curve. So basically, changes would start slow and then ramp up, and then slow down. So you don't have an abrupt start and stop. That's going to reduce damage to the belt itself, as well as the sheave. And it's going to reduce the stresses on the bearings. Okay, you notice here I'm already seeing bearing issues. And then also there's some other stuff having to do with, in this case, this is beforehand. Stator electrical defect was showing up out here because basically the drive had to be tuned a little bit better. So we took care of all of that while we were there. Winding stress still exists. That's a tuning issue. You notice these are at 4 kilohertz. There's the carrier frequency for the drive. Okay, and then I have all the frequencies associated with defects. And we're, basically at about 87 amps, 92 amps here. So slightly heavier load here at the point of testing because we couldn't control the load. We had to allow the static pressure for where it was being tested. It was a negative pressure application. So make sure I got these right. Yeah, 804, 925. So we went ahead and took a look at everything, and here's the losses associated with the original setting. So not too worried about pole pass frequency, and this is the unbalanced bit, and there was definitely some unbalance, maybe a little misalignment. So these have to do with the losses associated with the stator and rotor. And then as I come down here, you'll notice the opposite drive end is pretty high. So this is at 122% of load. So all of these losses combined come out to about 3 tons of CO2 per year and about $500. So this up here is the actual application. So it's overloaded, basically, because the nameplate calls for 71.2 amps, and we were definitely past that. And the reason for that has to do with the sheave sizes. The limit they had put on the drive allowed it to overdrive. So we had to leave it where it was, and the direct result was, relatively high skin temperatures on the motors. So we got an overloaded machine, basically. So let's go ahead and take a look at the other one. This is after we made all the setting changes. You notice that it's actually under a slightly heavier load. Speed, the speed is got even more slip to it now. So we have some stuff going on here, of course. Let's take a look at the losses here. In this case, that loss in that opposite drive end is still there. The other losses, some of them have dropped. I mean, these are basically down to friction losses, and when I'm at 40 some for this size bearing, that's an indicator that I have a defect. So I have problems in both ends of the bearings, and that's a direct result of the application. So 2 tons here at 130% load, and 3 tons here at a lighter load. So this would actually effectively be a difference of just over a ton of CO2 and probably a little bit more than that in value. Okay, so this is the one machine, and then we had a second machine involved, and that's this one. So this one here, same current draw, slightly different load, I believe, at the point. Yeah, 120% there, and this one 156%. So yeah, it's definitely drawing some current, right? Yep, 122 amps in a 70 amp machine. Now that's the average. So on the drive it was showing slightly lower, still showing overloaded, but basically they're overdriving the fan, and the horsepower requirement changes by the cube of the speed. So changing the speed just a little bit causes the current to go up dramatically. So they're trying to do whatever. After we made the changes, everything remained relatively constant. So the overdrive becomes an issue, in that it looks like we're using more energy now. We are technically, because we're overloading the machine. So that's going to end up being, once I make the changes, that's going to be a slight savings there as well. So what we did is we lengthened the ramp up time from about 60 seconds to 120 seconds. It took a lot longer to get up to speed, put less stress on everything. Well, how do I know there was stress? Okay, let's come back here, and I'm going to pause this just for a second. Now, quick preview on this, because we're going to look at some quick infrared images. I'm going to have to stop in between each one just because of the amount of lag I'm trying to avoid. But in any case, okay, so the center is going to be this white dot. Maximum is going to be the red, and blue here will be my minimum temperature. Minimum temperature, we were at about 20 to 22 degrees centigrade. These are all in centigrade. Okay, so that means that the temperatures are significantly higher. So about 55 degrees here, and let's go ahead and take a look at a couple other things. Now let's see if we can do it real quick, easy. Okay. So first, this is the bearing, roughly the bearing temperature on this application. That at the point we're testing, which has just started up, is about 34 degrees centigrade. Okay. And on the other machine, now this one has RS bearings in it. And I always tell people, why are you using RS bearings in a machine? Because it will cause the temperature to be higher. And as you can see, the housing temperature is 57 degrees centigrade. And a few seconds later, it climbs up to almost 60. Now, on the one machine, we had access to see the actual sheave. So as you can see here, the sheave itself has reached a temperature of about 47 degrees centigrade. Now, the shaft temperature has also come up, and that's going to be somewhere around 40 degrees centigrade. So the sheave temperature getting hot made the shaft temperature start to get warm. That, of course, causes the shaft to expand a little bit. And finally, even after being turned off for several minutes so we could get the cover off, the sheave and the other one is still right around 55 degrees centigrade. The end shaft close to the bearing, above the bearing, should say, is about 62 degrees centigrade. This is going to be somewhere close to that, and this is after everything's been turned off. So the concern is, where are we now? Well, again, had to make some significant adjustments. They still have to re-verify the alignment, because the alignment is critical in order for proper contact. The belt tension we're looking into, because the belt tension is obviously too great for the motors. We know that because we're seeing high friction losses on the bearings, right? So that's the opposite drive end ball, opposite drive end outer race, drive end ball. I mean, so that needs lubrication as well, but it's a non-lubricated bearing. Go figure. So that is primarily what I wanted to cover. And again, be cautious. Be very, very cautious. the energy savings we calculated on that application, if the speed was set right and everything else, was $100 or so a year, et cetera, et cetera, if it had been applied correctly in the first place. The misapplication increased the cost of operation significantly, has increased wear and tear on the machines. Now we have to figure out how to get the machines to operate within the range that they're supposed to, so we don't see a constantly overloaded condition. And with that, we will chat again next week. Next week, of course, being Thanksgiving here in the U.S. And we'll talk about something related to the holidays. Have a good one.